In this lecture, we will discuss the balance principle and its application for VLSI design. Balance as a universal principle will require all of the components, structures, parameters, and operation of different types in the system. So here are two real-time examples. The first one is really the balance of the rocks, which makes this rock last longer. If the rock is not balanced, it will be destroyed by natural force easily. The second example is the city traffic system. In this case, the balance of the bus direction allows the city traffic move smoothly. So now let's look into a few types of the balance. The first type of balance is called symmetrical balance. It is achieved by components of similar type. That means a ripple element. Solid balance also called formal balance. So here is one example of the formal balance. In this case, when the birds are flying, it is required to balance both of the wings, both left side and right side. The second type of balance is called a symmetrical balance. It is balanced achieved by non-reciprocal element. This type of balance is also called informal balance. So here are two examples. In the first example, when the birds are flying, the force to pull the bird forward and the force to pull backward will be balanced. In the airplane phase, the force to pull airplane up and pull down also be balanced. The third type of balance is called static balance. Static balance is achieved by the DC operation of the system. In this circuitry, this is the balance which makes the circuit stable. So the static balance is also called biased balance. Finally, we have the fourth type of balance, it's called dynamic balance. Static balance is responsible for the stability of the system in motion. And this static balance is also called active balance. So now let's look into how a balance principle can be used to decision making or decision training in our VLSI circuit design. Suppose we have two circuit elements X and Y, which are competing and positive elements. That means in one case, if the summation of X and Y are constant, so if the increase X will also ending with decrease Y or vice versa. In the second case, is the product of X and Y is a constant. So now let's look into the cost function where balance can make this cost function optimal. In the first case, the cost function is the summation of the X with the power n plus and with the summation of the Y with the power of n. In this case, the balance of X and Y will make this cost function minimum. In the second case, is the cost function is a product of the X with the power of n with the Y with the power of n. In this case, the balance of X and Y may make this cost function maximum. So now there are two application examples of this concept. In the first example, when we drive a large load in the digital gate with a big fan out, we can always break this into small pieces. In this case, we break into two with the fan out 1 and fan out 2. So now, by this balance principle, when fan out 0 and fan out 1 equals fan out 2, or that is means the fan out balance, this circuit delay are minimized. In the second example, when you drive a cylinder to a long distance on the chip, we can break this interconnect into two pieces with A1 and A2 as competing element because the total A1 plus A2 will be a constant, not total distance. In this case, the balance of A1 and A2 are also end of minimal delay of this interconnect driver circuitry. So now let's look into how balance principle can be used for decision making in analog circuit design. So now let's look at simple CMOS amplifier. how can we ensure high gain across all the pivot corner? So now the first one is really how can we balance the current bias, DC bias in the PMOS, NMOS. Second one is how can we ensure the amplifier always in high gain condition across pivot corner. So this will involve three critical decision-making thinking. The first one, we need to force the correlation of the biasing current in NMOS and PMOS. This one we're going to use in something we call current replica concept. In the second decision approach, is really how to force this MOS device always in saturation to ensure high gain across pivot corner. In this case, we're going to using something we call symmetric node group concept. In the third design thought is really how to ensure the current bias in the PMOS and NMOS, which are relatively stable, independent of power supply. So now let's look into how in the circle achieve the three critical thought. In the first thought, we're going to use a way to force the correlation between current in PMOS, NMOS, and a reference current from external across pivot corner. Here's a circuitry to implement this. In this circuitry, we have a PMOS set current mirror to ensure all the branch current are the same and which are tracking external reference IB. At the same time, we use an N-set current mirror to make sure all the current branch side are tracking this IB also. By doing this way, we are ensuring the current tracking of the amplifier PMOS, NMOS, that one are tracking external reference independent pivot corner. In the second design thought, how can we ensure the driver NMOS device always biasing in the actual saturation? Okay, so in this case, we are going to using something we call symmetric node group for high impedance node layout. By doing this way, we're using identical device M1 and M2 and the same biasing current for these two devices, even though in this case V out and VG are pivot sensitive. However, these two will track each other. And since M1 is always in saturation due to the direct connection across pivot corner. So now, since now V out and VG are symmetric nodes, in this case, this node will be tracking each other. So by doing this way, we ensure the M2 is always in saturation across the pivot corner. Also, by using this one, we also can determine what is the DC bias voltage of the output of the amplifier, which is basically VG or VG plus VG set. Finally, how can we generate a biasing current which are independent of the power supply? So here's one popular circuitry which I'll call constant GM biasing generating circuitry. Starting the circuitry have three basic components: NMOS, PMOS, and the resistor. And also the current in that circuitry can be derived as that are inversely proportional to beta n, that's the driver capability or drive string of NMOS, and R squared. So such circuitry can be said is independent or almost independent of power supply across pivot corner. And also, this circuitry can be converted into P-type circuitry for PMOS in the actual design. So now at the end of the lecture, let's look at the question of the day. So now if we're given OP impedance actual channel modulation effect lambda, what is a load pull-up pull-down current mismatch if we want to ensure the DC voltage bias of the output is within 1 volt? In second question, for this amplifier given of the what should be PN ratio to get the best linearity of the circuitry. In third question, how can we bias this amplifier input node G and output VL such that this amplifier is always in high gain condition across PV corner? The answer to these questions will be published in later chapters.